Moving hundreds of thousands of tons of steel and cargo through the ocean requires a massive expenditure of energy to overcome hydrodynamic drag. Before construction begins, designers must determine a precise technical requirement, the exact amount of engine power needed to push that specific hull shape through the water at its intended service speed. The financial stakes are significant. Overestimating power requirements leads to installing oversized engines, resulting in millions of dollars in wasted fuel over the ship's lifespan. Underestimating it is even more damaging. The vessel may lack the force to reach its operational speed, making it economically unviable. Historically, predicting this resistance was an imprecise craft. Naval architects relied on intuition and historical comparisons rather than a rigorous, predictive physical model. Accurately calculating hydrodynamic resistance is the mathematical foundation of maritime economics. It is the specific insight that allows for the construction of increasingly massive vessels. In the 1860s, British naval architect William Froude began a series of systematic hydrodynamic experiments to define ship drag mathematically. Between 1871 and 1872, Froude conducted full-scale towing trials using the HMS Greyhound, a wooden sloop measuring 172.5 feet and weighing 1,000 tons. He used a larger warship, the HMS Active, to tow the Greyhound through open water at speeds of nearly 13 knots. To ensure data accuracy, the Greyhound was towed 45 feet off the side of the Active using a long boom. This setup kept the test ship completely outside the wake interference of the towing vessel. Froude's goal was to validate his law of comparison. He hypothesized that the resistance measured on small-scale models could accurately predict the power requirements of a full-size ship. The Greyhound trials matched his 1/16th scale model predictions with high precision. By proving that model measurements scaled reliably to full-size results, Froude demonstrated that ship resistance was not a single, chaotic force, but a set of components that could be measured and scaled independently. This success relied on a specific realization. You cannot simply multiply a 1/100th scale model's total drag by 100 to find the ship's drag. The physics of water do not scale linearly. Froude defined total resistance, RT, as two distinct components operating under different physical laws. First is frictional resistance, RF, caused by viscous water dragging along the hull. Second is wave-making resistance, RW, the energy permanently lost forming waves. These forces must be calculated separately because they scale differently. Friction depends on the surface area of the hull, while wave-making depends on the ship's volume and the effect of gravity on the water surface. Separating these forces mathematically allows engineers to use scale models effectively. Treating them as a single unified force would make full-scale performance impossible to predict. Calculating frictional resistance, or RF, is the first step in determining total drag. Froude's formula is RF equals F times S times V to the power of 1.825. S is wetted surface, V is velocity. This relationship means drag increases rapidly with speed. F is the friction coefficient based on ship length. Froude determined these constants through thousands of physical towing tests with flat plates. Friction behaves predictably based on the hull's absolute length and wetted area. Because this friction follows a predictable mathematical path, engineers can calculate the friction of a model and subtract it from the testing data to isolate the other components. Scaling the second component, wave-making resistance, is more complex. Wave generation simply does not scale linearly. Gravity acts on a 3-foot model wave the same way it acts on an ocean wave, meaning the waves behave differently at different scales. To get accurate data, engineers must achieve dynamic similarity. The wave pattern created by the model in a tank must be perfectly proportional to the wave pattern of the full-size ship. Froude proved that wave-making resistance is comparable between scales only when the towing speeds are proportional to the square root of the ship's length. This chart shows the mathematical expression of this rule, the Froude number. The formula, V divided by the square root of GL, balances inertial forces against the downward pull of gravity over the waterline length of the hull. Running a scale model at the identical Froude number as the ship ensures dynamic similarity. This allows engineers to measure wave-making resistance on a small scale and project it onto the final ship with mathematical precision. In modern naval architecture, this historical methodology provides a specific step-by-step workflow for vessel design. First, the model is towed at its corresponding Froude number speed to measure total resistance. Second, Froude's formula calculates the model's frictional drag, which is subtracted from the total to isolate pure wave resistance. Third, that isolated wave resistance is scaled up to the full-size ship based on its displacement volume. Finally, the ship's frictional resistance is calculated independently and added to the scaled wave resistance for the final total resistance. By following this sequence, engineers can isolate the unpredictable wave variable and calculate the exact kilonewtons of force the real-world ship will encounter. This calculation determines the engine size, horsepower requirements, and daily fuel consumption, the primary economic and technical constraints for heavy multi-ton vessels. Froude's law of comparison remains the foundational principle of modern tow tank testing. By mathematically separating friction from wave-making, Froude established the scientific framework that scales the modern world's maritime supply chain.